Hello, so this is video number 3 of section 1.1. This video we want to look at 3 examples to answer 2 fundamental questions. And as you can see, fun is capitalized, which is a really funny joke because it's so original, because I turned the word fundamental into fun because this is so much fun. So the 2 questions we want to generally answer about linear systems. We want to know first, and you sort of answer these questions in order. So first we want to know, is a linear system consistent? So whenever we're given a linear system, we want to know, is it consistent? And remember, we call a linear system consistent if it has at least one solution. So if you remember from video 1, there were 3 possibilities for any given linear system. It could have no solutions, one solution, or infinitely many solutions. And so if the answer to question 1 is yes, so if consistent, is the solution unique? That is there exactly one solution, or are there infinitely many solutions? So whenever we're presented with a linear system, these are 2 of the fundamental questions we have, with the emphasis on fun. So all I want to do this video, all I want to do here is look at 3 specific examples where we will look at sort of each type of answer we can get. So we will look at a system that is consistent and has a unique solution, is consistent and has infinitely many, and then we will look at a system that is just inconsistent, meaning there is no solution at all. We will do so using our newfound tool of being able to use augmented matrices and row operations. And I will start to sort of give some ideas, and again, we'll start to, in section 1.2, we'll more formally kind of talk about a lot of this. But I will also start to sort of point out some patterns that you're going to see in a lot of the types of solutions we get. So we'll see that, especially with inconsistent systems and systems that have infinitely many solutions, there are 2 very distinct things that might happen with any system of that nature that we can sort of look for as we start to look at more of these linear systems. So today I want to start out with this system. So the 3 equations we have are x1 minus 2x2 plus x3 equals 0, 2x2 minus 8x3 equals 8, and 5x1 minus 5x3 equals 10. So I encourage you, try to use the methods we used last video to set up the augmented matrix to this equation. Use some row operations. Try and sort of fiddle around with using these row operations and try and find the solution to this equation. So pause here. All right, so setting up the augmented matrix to this system, I got the following. So here's the augmented matrix. And again, we want to use some row operations to turn this into a equivalent system, or find a row equivalent matrix using matrix terminology that makes finding the solution to this equation a little easier. And so remember, sort of the main goal here is to take row 3 and eliminate all other variables except x3. That is, get a 0 in the first column, a 0 in the second column, and maybe 2 values in the third and fourth columns. So first thing I'm going to do with that in mind is I'm going to do -5 row 1 plus row 3. So remember, this is the replacement operation. And again, this is replacing row 3 And so this leaves rows 1 and 2 alone. It puts a 0 here in row 3. It puts a 10 there. It puts a negative 10 there. And it puts a 10 here. And so now I'm going to do 2 operations at once. Both of these will be scaling operations. So I'm going to do 1/2 times row 2 and 1/10 times row 3. And that will get me the following matrix. All right. And so lastly, again, I want to now get rid of this 1, right, because I want to make x3 sort of the only variable in this last equation. So last thing I'm going to do is I'm going to do one more replacement operation. And I'm going to add negative row 2 plus row 3. And that gets me 1, negative 2, 1, 0, 0, 1, negative 4, 4. And finally, 0, 0, 3, and negative 3. All right, so I now have an equivalent linear system given by this matrix here. So I'm going to erase sort of the first step of this row operation to get it. So the equivalent linear system given to me by this matrix is x1 minus 2x2 plus x3 equals 0. 2x2, or sorry, I've divided by 2 here. So x2 minus 4x3 is equal to 4. And finally, 3x3 is equal to negative 3. And so now, again, because I've sort of worked this down to an equation with 3 variables, 2 variables, 1 variable, I can figure out the solution to the system, sort of working backwards. So x3 has to be equal to negative 1. If x3 is equal to negative 1, this means that x2 plus 4 is equal to 4. And so that means that x2 has to equal 0. Last but not least, I get x1 minus 0 minus 1 is equal to 0. And so x1 is equal to 1. All right, so this is yet another example, like the first example we saw in video 2, of a system that is consistent because we found a solution and has a unique solution. And so why does this solution have a unique solution? Why is this solution, the unique solution? So, sort of some intuition behind that. Notice that, again, performing all of these row operations, I start with this system and wind up with a system that is equivalent. And when I wind up with a system like this, where I go from an equation with 1 variable to an equation with 2 variables to an equation with 3 variables, if you can think about it, every variable is sort of being sequentially fixed in place. So here in equation 1, because I have the equation 3x3 equals negative 3, the value of x3 is immediately locked into place. Right? x3 has to be negative 1, otherwise the solution I get isn't correct. But once x3 is locked into place, that then leaves x2 in the second equation as the only variable, right? Because I know the value of x3 now. And so that then locks x2 into place. And once each of these variables are locked into place in equation 1, x1 is now locked into place. So when I work the linear system down to a matrix that looks like this, everything sort of gets sequentially locked into place, and I have a unique solution. That is, this assignment of variables is the only assignment of variables that will give me a solution. All right, so let's now look at a linear system that will have infinitely many solutions. So let's say I had the following linear system. So x1 minus 2x2 plus 3x3 is equal to 1. x1 plus 2x2 plus 7x3 is equal to 9. And 0 times x1, so 3 times x2 plus 3 times x3 is equal to 6. All right, so I want to now, again, use row operations to find the solution to this linear system. So I'm going to set up the augmented matrix. And again, I'm going to be starting by sort of working towards wanting to go for the same idea of eliminating variables in equations, right? So ultimately, I want an equation here that has one variable in row 3, right? So I want a bottom equation with just x3 as the only variable, a middle equation with x2 and x3 as the only variables, and a top equation where I've got x1, x2, x3. So the first thing I'm going to do here, and we haven't seen this step quite like this yet, I'm actually going to get rid of this 1 here in row 2. So the first thing I'm going to do is do negative row 1 plus row 2. And this will replace row 2. So row 1 is left alone. Row 3 is left alone. Now row 2, I get a 0, 4, 4, negative, or 8. All right, so next thing I want to do, well, I've already got a 0 here, which I eventually want. So in order to avoid losing this 0, right, I don't want to use row 1 to eliminate this 3. I want to use row 2 to eliminate this 3. So the next step I'm going to do is do negative 3/4 row 2 plus row 3. And this will replace row 3, but something sort of odd is going to happen here. So row 1 will be left alone. Row 2 will be left alone. Notice negative 3/4 times 4 is negative 3. So I get a 0, 0, 0. So at this stage, I've got the following equations. x1 minus 2x2 plus 3x3 is equal to 1. 4x2 plus 4x3 is equal to 8. And an equation of all zeros, which I guess you can interpret as 0 equals 0, but we already knew that, so this last row now really isn't adding anything. And so what we've done is we've sort of shown that in this original system, one of these equations was redundant, meaning that it didn't present us with any new information about the variables, right? And that's because I could use these two equations to sort of create this equation and work myself down to saying, well, if all of these 3 equations, any solution that works for these 3 equations will work for just these 2 equations. And so what's happened now is I've got 3 variables and only 2 equations that need to be solved. So, and I'll sort of pick a random value for x3, and I encourage you to try another one. I can pick any single value I want for x3 and find a valid solution to this equation. So let's say x3 is going to be, we'll do 2, since my favorite number is 2. So if x3 is equal to 2, I get the equation x1 minus 2x2 plus 6 is equal to 1. And I get the equation 4x2 plus 8 is equal to 8. And so notice I can solve the second equation to get that x2 is equal to 0. Solve this equation to get that x1 is equal to -7? No, x1 is equal to -5, sorry. But I encourage you to do the same thing, but pick something else for x3, and you'll see that we can still get a valid set of solutions to this equation. So what we get is that no matter what value I pick for x3, I get a solution, meaning there are infinitely many solutions because there's an infinity many of numbers I could pick for x3. And so what we see is that because we've worked this down to a matrix having a row of all zeros, I get infinitely many solutions, and we'll introduce this term formally here in a later section. But we actually can sort of think of x3 as being free. That is, we can assign whatever value we want to x3 and still come up with a valid solution to this linear system. So when we row reduce the augmented matrix and get a row of all zeros, usually that will correspond to infinitely many solutions. So this is a consistent system that does not have a unique solution. All right, so last thing we want to look at in this video is an inconsistent system. What will an inconsistent system look like? So let's say I gave you the following system. And so just looking at this system, you might be able to sort of see that this is going to be inconsistent. But we'll do the row operations here, and we'll sort of definitively show why we will get something that is inconsistent. So here's our system. I've set up the augmented matrix. Again, we want to row reduce this augmented matrix in the same way that we've been doing these row reduction steps, where I want to start by trying to eliminate all possible entries in this lower equation, except for x3 and maybe this final constant column, whatever that may be. So the way we've normally been doing this, well, I've got a nice 1 there in row 1, so maybe I'll add -1 row 1 to row 3. And again, we'll replace row 3. What happens when I do that? Well, I get 1, 0, 4, 1, 0, 1, 3, 2. So again, rows 1 and 2 aren't changed. I get a 0 here. That's what I was going for. 0 here. -4 plus 4 is 0. And here I get a 1. All right. So let's step back for a second and ask ourselves, what linear system does this correspond to? So again, the first two equations were never actually really changed. So this gives me x1 plus 4x3 is equal to 1. x2 plus 3x3 is equal to 2. 0x1 plus 0x2 plus 0x3 is equal to 1. All zeros there equal to 1. Well, this whole left side could be sort of condensed down to a maybe slightly easier way to read it. I'm trying to claim that 0 equals 1, which clearly it doesn't. And so notice if I try to use these row reduction steps and take my original augmented matrix and reduce it down to something that looks like this, where here the key thing to notice is I've got a row of all zeros with a constant. So row of zeros with a non-zero entry at the end. this corresponds to, because remember this last column, whenever I'm associating these augmented matrices with linear systems, this last column always corresponds to the right-hand side of this equation. But because I've got all zeros attached to the variables, this equation is always going to try to claim that 0 is equal to 1, which it can't. And so it turns out that any time I can row reduce a matrix and get something like this, that means that my system is inconsistent. And so this implies that the system is inconsistent, meaning there just is no solution. So, if you row reduce your matrix and each variable gets locked in, then you've got a unique solution. If you row reduce your matrix and get a row of all zeros, you'll usually have some variable which we might call free. That means that you have infinitely many solutions because you can pick whatever value you want for that variable. If I get a row of all zeros with a 1 at the end, or any constant at the end really that's not 0, I get an inconsistent system. All right, so that will wrap up section 1.1. With all of this, let me know if there are any questions. I'm happy to clear up anything that was not made clear in the videos. So you should be all set to do the problems from 1.1 that are assigned for the homework. And so let me know if there are any questions on any of that.